John and I are going to chat about a few things related to floods, and in fact, we're hoping that these will mesh together. Floods, floodplains, and functional flows is our topic. And we're, in fact, involved with two components to it. I'm going to talk about floods and flood history in Southern Alberta. John's then going to talk about functional flows and aspects of environmental flow regulation. Now, what I'd like to do is address two particular questions. Firstly, how exceptional were the recent floods in Southern Alberta? And secondly, are floods worsening or intensifying? Now, relative to the first question, in fact, the second as well, I'm not going to restrict the discussion to 2013, but I'd also like to think about the floods of 1995, especially in the Oldman Basin, as well as the 2005 flood that crossed both basins. Now, in order to consider these two questions, I'm going to take a look at historic hydrology. And what we have here is a map of Southern Alberta, and the circles with the crosses in it represent the particular locations that we're going to describe. We've actually analyzed historic flood flows for most of the tributaries shown in the map. I'm only going to present 4 hydrograph sequences or flood sequences this morning. At the top we have the Bow River, and I'll talk about Bassano, and the reason for that is that this is downstream from the tributary inflows from the Elbow and Highwood Sheep. I'll also talk about the Oldman. We're going to start with the headwater in Waterton. We'll move down to Lethbridge that also captures all the tributaries, and then we're going to combine the flows of the Oldman and Bow to provide the South Saskatchewan. Now, in terms of historic hydrology, hydrometric gauging began in Alberta about 1894. However, the early gauging was irregular and often focused on level without corresponding conversion to discharge or flow. By about 1901, partly affiliated with the international controversy of the transboundary St. Mary, there was gauging on both sides of the border, so we now have continuous records extending back to about 1902 for at least some of the tributaries in the Oldman system. By about 1908 or 1910, many of the streams were gauged. There were, however, some gaps, especially during World Wars and also during the Depression. Now, what we have here, in fact, is kind of an interesting sequence. This is the maximum daily mean discharge of Waterton, the Waterton River at Waterton. And this is a nice system because the headwaters are pretty pristine. This drains Glacier National Park, Montana, and Waterton Lakes National Park in Alberta. So the watershed is relatively unaltered. Some roads in there, not too much. There have, of course, been natural forest fires over the years. But generally speaking, it's a pretty natural series. And so if we think about time, if we think about climate change and time course, this is the type of reference that we want. These reference systems Paul and John referred to as well. And what we see here, in fact, is that most years the flood peaks are pretty modest. The annual peaks are pretty modest. But these then are occasionally interrupted with massive flows, many, many times higher than the otherwise mean. And Roger's going to talk a bit more as well in a couple of presentations. Now, the problem with this in terms of the statistics is that this is not, in fact, one distribution of high flows, but in fact is 2. So if we plot the recurrence estimates for the particular time series, 1902 to 2013, including 2013, the estimates for last year, what we see is that the flood series up to about the 10 or 15-year recurrence fits one relatively linear function. And then what we have is, in fact, a separate relatively linear function plotted on a log scale relative to recurrence. So we have a complexity here. We have 2 separate populations or distributions of flood series. This complicates the modeling, this complicates the analysis. If we try to fit this broken stick or this dogleg function with a single description, it won't work very well. Now, people have already talked about the weather event that leads to the floods in Southern Alberta, and this is the pattern. This is a satellite image, visible IR. And in fact, we get this pattern about every 2 or 3 years. And what we have then is, it's kind of interesting. I mean, you can see this massive cloud mass, and you can see it circulating counterclockwise. I've got the red arrow for this. That black dot is Lethbridge. Not that it's the center of the universe, but it's approximately where this thing swirls around. And as John and Paul have described, and others will again, what we have is a situation typically at the end of May and early June. The Gulf of Mexico is warm. We have a capacity for a lot of moisture to be coming up from that. And it's pretty much here at the junction of the east-west and north-south continental divides that we have the collision of the warm and cool air. And if this system stalls here for a few hours, we have a heavy rain event. If it stalls for a couple or 3 days, then we have a flood. I'd like to propose another possibility, and if you'll look at the covers on the description for the conference, it was great that the producers also provided a topographic contour map somewhat like this. The 49th parallel is approximately the north-south or Hudson Bay divide. And so if we look at the map here, wrapping around Lethbridge, we understand, in fact, that Glacier Park, Montana is mostly south and a little bit west, and then Waterton to the southwest and Crow's Nest to the west. And so the Rocky Mountains and also the extension to the Milk River Ridge forms a natural pocket, not unlike a baseball glove, that we believe contributes to trapping these flows or these storm events and maintaining. This is a little bit speculative, but it seems to make sense. There's perhaps a second weather pocket at the north end of Porcupine Hills that may in fact do the same thing. So what we had is flows of the Waterton River. We can now take a look at the subsequent flows downstream at Lethbridge. And what we find is that some of the floods persist. So we have some years in which we have high flows in the Waterton as well as downstream in Lethbridge. But we also have some years in which we have high flows originating from the west and northern tributaries, the Upper Oldman and Willow Creek, etc. But what you can also see then is, again, we have this complex two-part distribution. Lots of years in which the peak flows annually are pretty low, interrupted by the occasional, about every 10 or 15 years, that we have these pretty big flow events. Now, relative to the time series, we can be pretty confident of extending back to 1902. While we didn't have calibrated hydrometric gauges, we do in fact have pretty good stage data. And in the photograph in the lower left, we actually have some reference points that are pretty good. These are the footings for the high-level bridge, so we know exactly where the flood was in 1908. Now, as well, I've got a photograph in the bottom, in the photograph in the bottom, and then a note below this that in 1953 there was a flood that was substantial but not really extreme in Lethbridge, and it was again a situation in which the river valley was inundated and the developments there were flooded. And it was interesting that with the provincial and federal flood compensation in that cycle, there was a requirement that the residents relocated. So after 1953, Coalbanks or Lethbridge moved out of the valley, and today that's the case. And because of that, 1995, which was a much, much higher flood than 1953, had a relatively modest cost through Lethbridge. The Oldman we've already seen. This is the second plot, the Bow River again at Bassano. And what we can see then is that, again, there are some peaks that coincide, some that don't. These, in fact, allow us to map the extent of the inundation or the rain event. And as John indicated, it's not just intensity but duration, but also extent, how long across the watershed this thing occurs. If we think about putting these two together, but before we do that, you might also note that the y-axis is 1/2 for the Bow. In fact, the Oldman is a flashier system. It does, in fact, have these really high flows more often, and they are, in fact, somewhat larger on a per area basis. Putting these two together, we then end up with our composite hydrograph. And in fact, you see again the same pattern in which you have many years in which the high flow is fairly moderate, and then occasionally you'll have really high flow events. And relative to the question, how exceptional were Alberta's recent floods? We can put together a line, and in fact, the distribution approximately is split by that high flow in 1953. And what we see is 2013 in the overall basin was probably about the same, although slightly lower than 1902 and perhaps slightly higher than 1908. If you look at this distribution, there were two whopping big floods at the beginning of last century, and then recently we've had two pretty big floods. There were also two other moderate floods in the early part and the latter part. So basically, the flood of 2013 was indeed large, but it was not unprecedented. There were prior floods as large and at least slightly larger. Relative to this, we can then come up with the distribution, and what we have here is a table for recurrence estimates for the recent floods, 1995, 2005, 2013, and for reference, we have the 1902. Now, what I'd like to do is highlight the box in the lower right, and what you see are rather different estimates of the magnitude of recurrence relative to the 2013 flood. And the value on the right side on that table, the log Pearson type 3, this is the distribution that's recommended by the United States Geological Survey. But in our view, it doesn't fit our data very well. Instead, we have two other distributions that fit a lot better. The generalized extreme value is, in fact, the distribution recommended by the British Meteorologic Office, and we think that fits pretty well. Relative to that, we might then conclude that the 2013 flood was in the order of about a 1 in 75-year event. Relative to the overall watershed, it was more extreme relative to some particular tributaries. Finally, the second question, are floods worsening or intensifying? Well, what we have in the red dashed line is, in fact, this is a non-parametric fit with the Kendall test, and you can see, in fact, that there is, in fact, a statistical decline. But the reason for that is that in fairly low flow years, our dams do, in fact, trap and attenuate floods. So the big floods aren't really changing. We don't have a time series long enough to really answer that, and so it's apparently instead of not. But relative to the moderate high flows, these are in fact declining as a result of our regulation. This conclusion that floods are not intensifying is in contrast to a climate intensification theory that had some pretty interesting and solid foundation, but probably doesn't apply to our region relative to floods. And I have 3 papers cited there, fairly recent papers, that have similarly concluded that draining the Central Rockies, we haven't had intensifying floods. Now, relative to the floods, I've talked a bit about the occurrence, the duration, not the duration, but the occurrence over the last century or so. And I've got these numbers in green. And I've got them in green because ecologically, environmentally, floods are really important. And John will tell you a bit more about that.
I hate to be the bearer of good news, especially following Mayor Nenshi, who gave a very moving talk on the impacts on people and how the flood has affected people. I don't mean to belittle that by any stretch, but we need to realize that flood flows are a natural process. They've been around much longer than man has been on this earth, and they do things. And there are ecosystems that actually depend on these high flows. They're adapted to them. They're pulse-stabilized ecosystems, and they depend on them. And they don't actually mind too much when these big flows come through. So one of the things I need to talk about to start with are what are functional flows. This is probably a term you haven't heard, not too many people have heard about. We've talked about in-stream flow needs. There's a natural flow paradigm is something that's been talked about for many years. And the idea there is that when we have a managed river system, that we are deviating from the natural flow system. And when you have an ecosystem that's dependent on thousands of years of historical flows, that as we deviate from that, it becomes a problem. But we need to realize that we're not going back to where we were. There's too much of a human interest in maintaining our water structure. We depend on it for drinking water, for our industry, for our agriculture. And so we're not going to go back there. And so one of the ideas now is to take a more pragmatic approach and to identify those areas that are really essential for ecosystem support, and identify those functions that are supported by the various flows, and then use them to determine the kinds of flows that we should be releasing downstream from our management structures. So it's a conceptual framework to look at these ideas. And what it requires is that we have a solid understanding of the linkages between river flows and the various organisms, ecological processes that go on downstream from our water management structures. We need that knowledge to be able to make an informed decision. And then what we're trying to do, what the functional flow then does, is identify those flows that we want to be releasing to provide specific functions for ecological processes. So it's very targeted. It's no longer trying to go back in general terms to a more naturalized flow, although that may be part of it, but to identify those functions that we need to maintain. So for example, a functional flow may be defined for any level of flow. It may be the very lowest flows. So in that case, maybe we're just trying to support the survival of specific organisms. So provide the flows that will meet the temperature and dissolved oxygen demands of that organism. And that's all we're trying to do. So if you think of this as a stress situation, a naturally occurring drought situation perhaps, many organisms just barely made it through. And so that may be what our target is at that time. If it's a moderate flow, then maybe we're looking at something that's going to help sustain and encourage the growth or development of a population so that it can better withstand the impact of a drought situation or a low flow situation. And what I want to talk about specifically in the remaining time is a high flow situation. So these are going to be special events, as Stu's mentioned. There may be 1 in 10, 1 in 20 year events, unusual in the sense, and so they meet less common goals. So they may be flushing flows. So these are high flow events that are going to move bed load on a river. They will rejuvenate spawning beds for fish, for example. They may scour away macrophytes and open up the river channel to keep it active and keep the thalweg, the whole river meandering process moving. The one I'm going to talk about in the next little few minutes here is floodplain forest regeneration. So to do that, we need to, as I said, we need to understand how river flows and a particular process interact. And so this is something that we've been working on for over 20 years now, especially in the Oldman River Basin. We have a pretty good understanding with field work and with experimental work. And so what happens here, this is looking at the Oldman River downstream from Lethbridge, kind of near Tabor. There is actually a cottonwood grove behind the photographer in this picture. But what I wanted to show here was you can see various erosive patterns along the riverbank there. Up to about where the tripod is located, you can see there's several small little benches there. And that's the indication that that's where that river is mostly working. It's doing the erosion along that side. Once you get above the tripod there, you'll see that there's a little bit of woody stems. There's some willow and cottonwood growing there. And then as you get back past the stadia rod, there's another step up, and you can see that it's got quite a bit of woody vegetation along that side. And that's an indication that rarely gets inundated. There's not very much erosive power when the river gets up there. This is following 2010 event on the Oldman River, and the water did get up to the level of that bench above the tripod. And so what happens there, water got up to about this level, and so now the river is going to be depositing fine sediments in that area, and then as that river recedes, it'll be exposing moist barren substrate which is available for poplar seedling arrival. And as that river declines further, the seedlings or the seeds fluff lands there. And as the river declines further, those seeds will germinate. Now it's important to know that the linkage here specifically between the seedlings and the river is through the floodplain water table. And so the water table in the floodplain is directly linked with the river stage. And so we know that as the river stage declines, the floodplain water table pretty closely matches that. We also know that the seedlings can put down their roots at about 4 centimeters a day. And so if the river stage goes down at rates greater than 4 centimeters a day, the seedlings will lose contact with that water table, and then in the absence of rain events over the course of the summer, they will desiccate and die. So they're really finely attuned to the occurrence of the flood events, large flow events, and the rate of decline subsequently. So a functional flow then that we would be targeting for this particular issue would be to have a declining stage of about 4 centimeters a day. So we've been applying this in the Oldman River Basin for a number of years, and we've been working on the Oldman River Dam, the St. Mary Dam, and the Waterton Dam, and we find it's not all that easy to actually do. We're getting pretty good at it down that area, but it's difficult, and so the idea here was to look at, well, what happened on the Bow River, and how close were we able to manage those flows and generate a benefit from here. Now I need to point out, TransAlta has never tried this before. It was never intended as part of their management structure this year. They had a big flow to deal with, and they did very well with it. So this is a retroactive look at it to see whether or not there's any opportunity here at all. Oh, so this is what a site might look like where it was successful. This is actually on the Waterton River. You can see in the foreground fine sediments and wet that have been deposited, and we see that there are actually poplar seedlings occurring there, those very small clusters, and then if you look in between the willows there, you can see single individual seedlings scattered throughout. So the Bow River at Calgary, you'll notice that this graph, first of all, doesn't talk about flow, it talks about river stage. I'm interested in the rate of decline, so I don't care if it's 2,000 or 21 or however cubic meters per second, that makes no sense to me. I need to know what that river stage is doing. The green line and the red line are the upper and lower quartile flows to give us a sense of where the normal flow is through the Bow River at Calgary. And you'll notice that even though this is the prime time for flooding events in Calgary, there's no little blip on the upper quartile flow. And if you think back to the images that Stu provided, it's only those top 10 or 15 flows that I'm actually talking about here. And so they're so much larger than and outside of the normal flow range that they're not sufficient to bump that upper quartile flow up. So here's what happened, and this is a variation of what you've seen a number of times. You'll see many more times, I'm sure, over the next 2 days. Significant high rise in river stage, fairly short duration peak, followed by rapid decline. And then interestingly, around about near the end of June, you can see that we got down to a river stage of about 2¼ meters. And that's probably pretty near bank full, or it's at a level that TransAlta identified as being acceptable, and they're going to maintain that level for as long as it's necessary to get full control back into the system. And then there was a ramping flow following that. So my area of concern then is for this, from this point forward, and looking at this, and so we go, what is a 4 centimeter per day rate? And if we look at this one, the light blue line indicates a 4 centimeter per day rate, and we see that actually it's pretty good. The flat stretch along the from the star to the blue line is okay. It's less than 4 centimeters a day, so that's fine. And then a ramping rate down of 4 centimeters a day. And if we look at it in detail, we can see that the average rate of river decline was 3 centimeters a day over that period, so much less than 4, so that was good. And we find that there's a compliance rate of about 75%. This is very high. We find in the Oldman Basin that anytime we get up above 80 to 85% is about as close as we can get it, and simply because there will be single days here and there where the flows will decline at a much higher rate. So my conclusion then for this, even though there was no attempt to try and generate flows that would be supportive of this particular function, the TransAlta actually did a very good job in actually achieving that. And so what that suggests then is that there may be an opportunity in this situation to add a conceptual functional flows to their framework, their management framework, and they may be able to apply it on an ongoing basis. And that's all.
Thanks for the presentation. The objectives that you talked about at the beginning with the riverbank vegetation regeneration, how would that compare to the flushing objectives? Like, are those still kind of out of reach in terms of the channel scouring, that you know, the benefits of that?
No, the flushing flow requirement is generally much lower. All it requires, it's typically somewhere around bank full or slightly below, is a rule of thumb. So in this situation where we went well above bank full, that would have met that function as well.
Carolyn, I might add that to some extent floods provide an opportunity, and in some systems with really big reservoirs, floods have been fully attenuated. But in Southern Alberta, apparently they're not. And so in terms of some of the high velocity functions, these things still persist independent of what we do.
Stu, your maximum flows for Medicine Hat that you added, the Old Man and the Bow, were they just simply the maximum for the Old Man, maximum Bow added, or was there adjustment? Let's say one was June the 10th and one was June the 30th.
Len, these were actual measurements, and relative to, there was a little bit of splicing relative to some of the values, but there were stage measurements for the 1902 and 1908 floods at Medicine Hat. There were also at Saskatoon as well. And in fact, Salfig-Liuzzi's done a pretty good job of reconstructing. So these are not simply added, these are the corrected stage measurements, and then from those, the deduced discharge measurements. So no, it's not simply adding A plus B, it's actually finding out what the discharges were at South Saskatchewan. So I think that time series is pretty good.